This is A2 Module 4, January 05. And again, this is a question on Young's modulus and Hooke's law. This was a question 1. And this was a fairly stringent question asking you to draw out the apparatus you would use to determine the Young modulus of a metal in the form of a wire. Now I'm going to cheat here and not draw it out. And I'm going to use the diagram on your front cover of your booklet, which is the diagram showing you this here. So I'll just put this up a wee bit and come out a little bit. So hopefully you can see this. You've got 2 wires. This one is a reference wire. There's a support at the ceiling and a reference wire. At the bottom of the reference wire you have the scale or the ruler, and you have a weight at the bottom to keep the reference wire tight. The second wire is the one under test, so call it the test wire. This is a vernier scale, and down at the bottom you've got a load hanging on it. And you could also measure or indicate where the length of the wire is, and the length of the wire is from where it is supported up here down to where the vernier starts down here. And that's the length of your wire. For your marks in that question, they wanted a wire clamped at one end, which is this one here, with a load on it, a way of measuring length or extension, and so this is our way of measuring our length or extension, and a reference extension marker in the last third of the wire. So in the reference wire there should be an extension marker, and it should be in the last third of this wire here, and that is the case here. Okay, and I'll be using that diagram a couple more times, so it's really worthwhile learning that diagram. I'll just scan in a wee bit so you can see all the details of it. So there it is at the top. Show a support from a ceiling or a bar, whatever. Ours was from our steel beam in the classroom. Then show a reference wire and a test wire. Label a scale, label a vernier, label a weight to keep the reference wire tight, and label a load. So just learn that diagram, because you're asked to draw that quite often. Just scan out again. Measurements required for this determination include the original length of the wire, its extension when a load is applied, and the area of the cross-section of the wire. Explain carefully how in the apparatus you've sketched these quantities are obtained. So how do you get original length? You measure using a ruler the distance between support and it calls it a reference marker. I would call it the start of the vernier scale. I'm going to put that in there, start of vernier scale. Your extension E then, the extension E is measured again using some kind of ruler. In this case it's a vernier scale. And the extension that you're measuring is the increase in length. So it's original to the final position of the vernier scale. The area of cross-section A, so you can see there's 3 marks here, so there's going to be a little bit more detail required. So first of all, you will measure the diameter of the wire. And we're going to write in 3 places and calculate an average. And you're going to use a micrometer screw gauge and then you're going to calculate using A equals pi r squared, and that's equal to pi times d over 2, the diameter, average diameter. Part 3. Assume that a series of values of extension E has been obtained for different loads F. State how the results should be processed to obtain the Young modulus capital E by a graphical method. So I've written down our equation. Young modulus is stress over strain, so it's sigma over epsilon are the letters that we can use, which is equal to force over area divided by, I wrote extension there as an X, I suppose I should have written it as an E, and I'll just maybe rewrite it here. So that's F over A, and that's divided by E over L. So if you plot, if I just show you down at the bottom here first of all, if I rearrange that, extension over length, so we had E is equal to F over A divided by X over L. You bring your X over L over here to multiply E. You have X over L times E is equal to F over A. And then that means if you put that on the y-axis and this on the x-axis, and the gradient of your graph will give you M. So that's what you need to explain. I should have, of course, changed that into an E there, a small e, because I've used an E in the question. So that's what you have here. You've got F over A values on the y-axis, X over L values on the x-axis. That should give you a straight line through the origin, and then Young modulus should be the gradient of your graph. So that's where your 3 marks are coming from there. And then the next part of the question is a calculation. I'll just scan out a wee bit here. Aware of length 3 metres, I've written that down, and diameter 2 millimetres, so 2 millimetres is a diameter. To get an area, that's pi r squared, but r is equal to d over 2, and therefore that's pi 2 by 10 to the minus 3 because it's in millimetres divided by 2, and that's all squared. It is stretched with the application of a force of 491 newtons. The Young modulus of the material of the wire is 1.8 by 10 to the 11 pascals, and we need a value for extension. And so if I just write down the equation I had written over the page, I had F over A, and that's divided by, and I'll write it as an E over L. And we need a value for E, so that's equal to, that's the same as dividing by a fraction upside down. If you're dividing by a fraction, it's the same as multiplying by it upside down. So that becomes F times L over extension times area. And then if we need a value for E, all we need to do is swap E and capital E over FL over EA. Okay, so I'll scan in a wee bit there. So E is equal to FL over E times A, and F is 491, L is 3 metres, E is 1.8 by 10 to the 11, and A is I know I'm just writing it as pi times 1 by 10 to the minus 3 squared, and that gives you an answer of 2.6 by 10 to the minus 3. Which is the same as 2.6 millimetres. And so it's 2.6 by 10 to the minus 3 metres.